Alright, so in this video we're going to be looking at the same molecule that we looked at in the previous video, but we're going to throw this in basic conditions now instead of acidic conditions. We already know what's going to happen. We know that in basic conditions, bromine will go in and replace every single alpha hydrogen that we have on the molecule with the halogen. But we have to understand why this happens. Why does a base environment promote the substitution of all of the alpha hydrogens when an acidic environment does not? Okay, so again, we got to take a look at the mechanism in order to understand why this works and how this operates. So we're going to start off with just the molecule, and again, I'm just going to pull the hydrogen down here below because that's our focus now. We're looking at alpha carbon attack. And we've got this bromo that I'm not going to write yet. And we also have this OH group, this some kind of base that's in solution, and I'm just going to write it down here at the bottom. Okay, so I want to kind of look at how these two things interact, and this base is strongly negative, and this is going to actively look for a positive piece in the molecule, and one of those possibilities is a alpha carbon and the alpha hydrogens, because we said that this thing is acidic. So here I have an alpha carbon, and this alpha carbon, if this hydrogen can be pulled off, has some electrons now that can be shared throughout the entire molecule, and we get some delocalization because of that, which is a good thing, like in the words of Martha Stewart, for the molecule. So I want to show that step. You know, this OH is going to look at the alpha hydrogen, pull off the acidic alpha hydrogen, and when that happens, these bonding electrons will go in between my two carbons, but I kind of want to take it baby steps at a time, right? So I'm going to show that these electrons can go here, and if this double bond forms at that location, then those electrons can be shoved up. And if those electrons can be shoved up, then all of a sudden we have a negative oxygen up at the top. So this CH is now a double bond C that has a single bond OH, or sorry, not an OH yet, I'm getting ahead of myself, an O with a hydrogen, and this oxygen is now negative. And the reason for that is because it gained the electrons in the double bond. Okay, so now we have this C double bond C and this O with a negative out there. And this is what we call the enolate ion. It looks kind of like an enol, right? And if an enol can rearrange, then guess what? An enolate ion can rearrange as well, because that really idea never goes away. So we see some tautomerization that can happen, and this oxygen says, oh no, carbon, you gave me a negative charge, and I don't really like this negative charge, and I'm sorry, but you're going to have to take these back. So that's the story that always happens with oxygen. So oxygen shoves the electrons back, and carbon says, okay, fine, if this is what I have to do, then I'm going to have to break my double bond, and I'm going to revert back on myself. Well, not quite yet, because in this solution we have Br2, right? So the story with Br2 still the same. London dispersion can happen. We can see a slightly positive bromine that could come around if it needs to. So this double bond of the carbon, well, that double bond can break, and those electrons can help pull one of these bromines off, and then bromine will take the other set of electrons and go. The same thing happened with the acidic mechanism. So far, the only difference that we have seen is the base is attacking the alpha carbon first. In the acidic conditions, the acid attacked the oxygen first, because that was the negative part for the acid. Well, we have a negative piece we're starting with this time that's attacking the hydrogen in the very beginning. So now that we've done that, we can draw the product that forms after this takes place, and that's CH3, CH with a Br now, and then a carbon that has a double bond O, and then the hydrogen. Okay, so this is kind of where the acidic mechanism would stop. It wouldn't go forward anymore once that first bromine comes on. However, this is a base environment, which means that we have more OH group that's in solution. So we get a OH group that maybe comes back into the picture, and it notices that this carbon now has another hydrogen that it could give up. Okay, well, here's the major difference in this spot, because I mentioned in the previous video that the presence of this bromine prevents the acidic mechanism from going forward. However, it's not the same in the basic environment. The OH will come back in, and the OH group will pull this hydrogen back off. The electrons will shove here. The oxygen electrons will go up. Oxygen will revert the electrons back down. The double bond that forms here, well, there's another bromine in solution, right? So we get another Br2. So the double bond that's formed here is going to be broken, and it pulls one of these bromines off, and the other bromine takes the electrons and goes. And we end up with another substitution reaction in a way. So a bromo there, a bromo here, and then the C double bond O with the hydrogen. So this will repeat. So up here at the top, I'm going to write the big word repeat until no more alpha hydrogens. Okay, so here's the story. These steps will repeat until every single alpha hydrogen is replaced by a halogen. Not only that, but every time it repeats, each repeat step is more rapid than the first. So I'm going to put a big exclamation mark and a big question mark there, because this kind of contradicts what we said in the previous video in a way, right? I mean, bromo is there and bromo cause problems in acidic environment, but in a basic environment when bromo is there, this actually speeds up the reaction after that one is on. And that is, yes, because the halogen, the bromo or the chloro that goes onto these molecules, they are electron withdrawing. So if I look at this bromo group, we are going to call this electron withdrawing, right? It is electronegative, so it's an electron sucker. And that increases the acidity of the remaining alpha hydrogens. And that is why all of the alpha hydrogens get replaced. Okay, so bromo or chloro's electron withdrawing, let's make sure that we're very clear on this before we go forward. This increases the acidity of the alpha hydrogen, and because of that, the reaction goes quicker. It's easier to remove those hydrogens from there. Okay, well, what about acidic conditions? We said that it only happens one time, and that is it. How is that different? Okay, well, with the acidic condition, when my first bromo or chloro goes on, like we said before, that bromo is going to slow down the reaction. Okay, so now you're probably questioning, well, why? I mean, a bromo's a bromo group. Why does bromo in an acidic environment slow down the reaction, but a bromo in a basic environment speeds up the reaction? And that's because bromo here, or chloro, well, the story still is it's electron withdrawing. It is true, it is electron withdrawing. But what happens is that in an acidic environment, the acid is focused on the oxygen of the carbonyl. In the base environment, the base is directly focused on the hydrogens and pulling the hydrogens off. That's not how the acid mechanism works. The acid does not focus on the alpha hydrogen, pulling it off in the first step. The acid focuses on the oxygen of the carbonyl in the first step. So once the first bromo goes on, you can't remove that second alpha hydrogen because you have to rely on the acid to attack the carbonyl again. So once the first halogen goes on, you actually decrease what we call the basicity. B-A-S-I-C-I-T-Y. The basicity of the carbonyl oxygen. And if you make it less of a base, the acid is not attracted to it as much. So it makes the protonation of the carbonyl a little bit harder. So it's going to be harder to protonate the C double bond O in the first step. And that is the major difference between acid and base mechanism. Acid mechanism focuses on the carbonyl. And if we lower the activity of the carbonyl and make it uglier, the acid has a harder time, or it's less favorable to attack that oxygen. And we have to rely on the first step of the mechanism for this bromo to go onto the molecule. However, with a base environment, well, the base environment, it doesn't really care about the oxygen in the carbonyl. It's not even looking at it. The base is looking at the acidic proton, and as long as there is an acid proton there, it's going to keep attacking it, and it's going to keep pulling it off. So those are the major differences between an acid and base mechanism as far as halogenation goes. That is why acid only replaces one, because you lower the activity of the carbonyl, and that's why base replaces all of them. And that's because you're looking at solely the alpha hydrogens that are in the molecule. Alright, so in the next video, we're going to be looking at something very similar. We're going to be looking at halogenation, but we're going to look at halogenation of a carboxylic acid because that's a little different. Here we've only focused on ketones and aldehydes. That's really it. Type 2 carbonyls halogenating a type 2 carbonyl. We see an alpha hydrogen that can be pulled off. In the next video, though, we're going to be looking at a different type of reaction that will focus on carboxylic acids. We'll talk about why we see a problem with them next.